All right, well, welcome to our last week. This is our last official week for final exams. And so we're here. I'm not really following the schedule anymore, so I guess to make up something, I'm still doing 5-5 here. So some of 5-5 today, some of 5-5 tomorrow. And Wednesday, our usual question and answer. Test again this week is on Thursday, not Friday. Friday, I'll reserve for questions and answers in preparation for the final exam. Okay. And so this is our last regular week. Next week, we don't meet on Monday. We don't meet on Tuesday. Final exam is Wednesday from 11:10 to 1:40. Okay. You don't have to turn in any homework for the final exam. You do have to turn in the homework as usual for this last test. So as usual, you turn in all of this by Thursday. But you don't have to turn any homework in for the final exam. Okay. Final exam will be questions similar to the previous exams. Okay, so let's say we have 5 tests. Maybe I'll give you 3 questions each. 3 times 5 is 15, or maybe 4 questions each. 4 times 5 would be 20 for number of questions on the final exam. Okay, just bring all the former cheat sheets, all the formula sheets that you had for test 1, test 2, test 3, test 4. Hopefully you still have them. If not, you can redo them. And you're building the cheat sheet for test 5. You just use them all for the final exam. Okay, so for the final, as usual, I will email to you, or rather send it through Canvas announcements a little bit after 11, and then you'll join me, and you have 2.5 hours for the final exam, and then that'll be it. Okay. I also just recently sent you a modified office hours for me. It affected Thursday, and you're probably not going to join my office hours Thursday because we're done by Wednesday, but I'm legally supposed to show it to you, so I sent that to you on Canvas announcements in case you want to catch me during final exams week. Okay. All right, so we were doing substitution. I did very few last time, so I'll do more substitution today. I'll do more substitution tomorrow, basically with definite integrals. So maybe I'll show you one. It's a little bit different with definite as opposed to indefinite integrals. Okay. All right, so that's where we're headed, and we're almost done. Okay, I do know some of you sent something through the chat, so let me see if I can check that quickly. Let's see. Yeah, so if you join late, just send me an email later. Are you allowed to print out the final? Sure. When I send it through Canvas announcements, go ahead and print it out if that's better for you. You certainly may do that if you have a printer. That's okay by me. Okay, let's see. The quiz. It's not too late to submit the quiz, so hopefully it wasn't too bad. Okay, number 1, 2x to the 4th over 4, 7x squared over 2 from 0 to 6. This comes out to be x to the 4th over 2 plus 7x squared over 2. Plug in 6, a little bit of work. Plug in 0, there's no work at all. It's all 0. 774 if you do it the right way. Number 2, integral of the sine is negative cosine. Integral of cosine is sine from 0 to pi over 2. Plug in pi over 2, you get 0 plus 1 minus plug in 0, negative 1 plus 0 comes out to be 2. Okay, number 3, integral of e to the negative x is negative e to the negative x. Integral of 1 over x is natural log absolute value of x from 1 to 5. Plug in 5. Negative e to negative 5 plus ln. Okay, some of you put absolute value of 5 and left it that way. You don't leave your final answer as absolute value 5. Now, you do need to show me absolute value here. That's properly antiderivative 1 over x. So, again, ground rules, integral of 1 over x is ln absolute value of x. But when you plug in 5, you shouldn't leave it as absolute value of 5. Absolute value of 5 is 5. So your final answer should just be ln 5. Okay, minus negative e to negative 1 plus natural log of 1. Natural log of 1 is 0. So best final answer is e to the negative 1 minus e to the negative 5 plus ln 5. You are allowed to stop here. If you want to keep going to 1.97, that's okay. But you must show me exactly this. Okay. So it's not considered full credit if you show me this, unless you also show me this. Okay. So I let go the absolute value here, but I may not be as generous on the exam. Okay. So the whole idea is to write your answer simplified. To write the answer as ln absolute value of 5, that can be simplified, right? So, this should not be an acceptable final answer because the absolute value of 5 is 5. Okay. So again, for the antiderivative part, put ln absolute value of 5. But your final answer, what is the absolute value of 5? 5. So you should write it as just ln 5. Okay, so that was the quiz. That was our last quiz. We have 12 quizzes. You get to drop 1 out of every 4. So every 4 quizzes, you get to drop 1. That includes if you missed a quiz. Okay, so that is that. All right, so back to substitution. So again, we're looking for a function and its derivative, and then do a u substitution. All right, so look for a function and its derivative, or maybe the derivative times a constant. Okay, so last time I got up to 7. I'll do many more. Okay, so let me show you 11. Integral of cosine pi t over 2 dt. Now, you want to think of this as the coefficient being pi over 2. Pi over 2 is a number. It's like 1.57 or something like that. Okay. So pretend it's cosine 1.57 t. Okay, you can actually do this without the u substitution. I'll talk about it quickly in a second. But let u be this. The whole idea being I'd rather integrate cosine of u, not cosine of all that. So u equals pi over 2 t. du, what's the derivative of this? Pi over 2 dt. There's dt. I don't have the pi over 2. It's a constant. Just put it in. Pi over 2 inside, 2 over pi outside. Okay. And a lot of you are still worrying about this step. 2 over pi times pi over 2 is equal to what? It's equal to 1. If I multiply in any math expression by 1, I get an equivalent expression. Okay. You can't just arbitrarily out of nowhere multiply by pi over 2, multiply by 1.57. That does not give you an equivalent expression. Okay. I can multiply by 1. Here's 1, 2 over pi times pi over 2. Okay. But why did I put the pi over 2 in the first place? I can't substitute for du until I see pi over 2 dt. Once I see pi over 2 dt, I can make that du, and this is my u. So my new integral, again, what's my capital I? Capital I is my notation for the original integral. Okay, so that way I don't have to write the original all over again. Okay, I'll just warn you, other teachers don't do that. So those of you going on to Calc 2, which I'm assuming many of you are, your Calc 2 teacher may not use a lot of the notations that I do. Okay, but they might write the whole thing all over. I don't feel like writing the whole thing all over. I'll just call it I, and my definition is I is always the original integral. Okay, so that's my rules, as it were. Okay, so 2 over pi, integral of cosine u du. Okay, what's the integral of cosine? Sine. So 2 over pi sine u plus c. Then finally change u back to pi over 2. So 2 over pi sine pi over 2t plus a constant. Okay, problem's finished, but I'll dig a little bit deeper. This one you can do without a u substitution just by thinking backwards of what you do in terms of differentiation and integration. Okay? That trick works when you have constants but not variables involved. If you have to multiply inside and outside by a constant, you can do that. You can't do that for a variable. So what's not allowed is, say, multiply inside by x and outside by 1 over x. That's not allowed. Okay? You want to ask why isn't it allowed? Well, you can double check. If you go ahead and take the derivative of what you end up with, it isn't going to be the same thing. Okay? Unless you have a constant. It works for constants. Okay, so since the chain will only use a constant, let's think of it this way. Okay, if I were to ask for the derivative of cosine pi over 2t, you would say cosine pi over 2t, then by the chain rule times pi over 2, right? So keep that thought, multiplied by pi over 2. Therefore, what happens when you integrate? You don't multiply by pi over 2, you would divide by pi over 2, which means multiply by 2 over pi. Okay. So for this particular problem, that would be a faster way to think of this problem. Okay, but you can't do that if variables are involved. Okay, so if that trick would not work, let's say for problem 5 that I did last time, since there's x to the 4th and x cubed, you have to do the u substitution in this particular case. When a constant is involved, can you say, okay, multiply by pi over 2 when I differentiate, therefore multiply by 2 over pi when I integrate. So that works in this case. Okay, 15. Cosine cube theta, sine of theta, d theta. Okay. Now, at first glance, you might think you have a choice. Integral, integral of cosine is sine. Integral of sine is cosine, almost. They're sort of derivatives of each other except for the negative one. Now, if I did a u substitution, let u be sine theta, du is cosine theta, but I don't have cosine theta, I have cosine cubed. I have more than I've bargained with. So that would not be the way to go. Instead, let u be cosine theta. Not cosine cubed, just cosine theta. The derivative is negative sine theta d theta. That's okay. I can put a negative 1 inside and outside. And you say, what about the 3? That's okay. I'll be left with u cubed. I don't mind integrating u cubed. U cubed is very easy to integrate. Okay, so one more time. I don't want u equals sine theta because the derivative is cosine theta d theta. I don't have cosine theta. I have cosine cubed theta. So I can get rid of cosine theta, but I still have cosine squared left over that I can't get rid of. Instead, let u be cosine theta, not cosine cubed. If I let u be cosine cubed, when I differentiate, I'd have to do the chain root. I don't want to do the chain root unnecessarily. Just let u be cosine theta. You'll be left with u cubed, but that's easy to differentiate. That's easy to integrate. So let u be cosine theta. Du is negative sine theta d theta. The original has sine theta d theta. No big deal. Put negative 1 inside, negative 1 outside. That way, all of this becomes u cubed. All of this becomes du, and there's a negative sign in front. That's fine. So negative u to the 4th over 4 plus c. Change u back to cosine. So final answer, negative 1/4 cosine to the 4th theta plus a constant c. And there we go. Okay. Side note, let's differentiate this. What's the derivative of this? 4 comes down and hits the 1/4. So you'd have a negative 1, right? So if we can just pretend there's a negative 1 there, it'd be cosine cubed. There it is. Then by the chain root times the derivative of the inside. Derivative of cosine is negative sine. That negative knocks out that negative that was still there. You have that exactly. Cosine cubed theta, sine theta, d theta. Right? Remember, how can you always double check any integration problem? By differentiation. Right? If you differentiate, you get what you need. Okay. All right, so that's it for that one. Okay, now continuing on to more. 5.5 into 21. ln x squared over x dx. Right. What's the derivative of ln x? 1 over x. Perfect. Here it is. You say, well, there's no 1. You can always sneak in a 1. ln x is 1 times ln x, or ln x squared, actually. Right? So you can sneak in a multiplication by 1. So here's a function. The derivative is 1 over x. There it is. So it's in red because it wasn't in the original problem. So there it is. U equals ln x. Du is 1 over x dx. So my 1 over x dx, the next step will be du. The next step, change this to u. I'll have u squared du. And that's easy. U cubed over 3 plus c. Change u back to ln x. So final answer, 1/3 natural log of x cubed plus c. And by the way, you do need parentheses. It's not the same thing if you leave the parentheses out. If you leave the parentheses out, then the understanding is ln x cubed, which is not the same thing as this. Right? ln x cubed means ln x times x times x. This means ln x times ln x times ln x, and they're not the same. So this is what you want. And yeah, I declare this should be pretty easy to double check. Let's differentiate. Derivative of any constant is 0. 3 will come down, knock out the 1/3, it's gone. ln x squared, there it is. And then by the chain root times the derivative of the inside, which is 1 over x. Perfect, there it is. All right, 31. Arctangent squared over x squared plus 1. Dare I say this is almost tailor-made, pretty much set. Here's a function, arctangent, whose derivative is 1 over x squared plus 1. Again, you say, I don't see the 1. You can pretend there's a 1 there, right? Multiplied by 1. So it's perfect. Let u be arctan x, which is the same as inverse tangent of x. So they write it like this, or they write it like that, same thing. This is a little bit shorter to write, but this is easier to type, right? If you have to type on your keyboard, it's, you know, A-R-C-T-A-N. Unless you have special software, it's kind of hard to get that -1 on your keyboard, right? So this is a little bit easier to write. This is easier to type. So du is 1 over x squared plus 1 dx. Perfect. Don't need to multiply by any constant. U squared, or u squared over 1, which is just u squared, du. Okay, so u cubed over 3 plus c. Substitute back. What was u? Arctan. So 1/3 arctangent cubed plus c. Okay, next one I was going to show you is 41. Cotangent. Well, cotangent is cosine over sine, and now it's perfect. Perfect for my u substitution. You have a function and its derivative. Actually, you might be confused and say, which one should I do? Because the derivative of the sine is the cosine, and the derivative of the cosine is almost the sine. But here's the key. You don't really have sine x. You have 1 over sine x. That tells me not to let u be cosine x. Okay, so again, if I let u be cosine x, the derivative is negative sine x, but I don't have that. The sine x is in the bottom. Cosine x is on top. So that tells me I should let u be sine x. I will end up with 1 over u. That's okay. That doesn't bother me. So u equals sine x. Du is cosine x dx. I'm going to have 1 over u, or du. All of this is du over u. That's fine. That's perfect. You can pretend there's a 1 there. I'll leave it out so you can get used to seeing it du over u. You should say, oh yeah, that's my natural log, right? There's a pretend 1 here. 1 over u, right? So ln absolute value of u plus a constant. Change u back to what it was. So final answer, ln absolute value of sine x plus a constant. So the antiderivative of cotangent is this. And by the way, side note again, this is very easy to check, right? The derivative of ln absolute value of something is 1 over that. So 1 over sine x, right? Pretend there's a sine x on the bottom, times the derivative of the inside by the chain root, which is cosine x. So I have cosine x over sine x, perfect, cotangent x. Okay. All right, so I did a lot more of the indefinite integrals. Okay, there's still some indefinite integrals I want to try, but I want to show you some definite integrals now. I still have tomorrow to go back and do some more indefinite and definite integrals. But starting with problem 53 at the bottom there, 53 and all the rest, okay, there's a slightly different technique when you're integrating and substitution for definite integrals. I mean, what are definite integrals? There are definite numbers here and here. So the final answer is not blah, blah, blah plus c, we said. The final answer is a real number. Okay, so how do you do that? Okay, and I'm just noticing something. I'm going to throw out problem 61. It's a little bit different. Okay, so skip 61, please. Skip 61, 5.5. All right, so I wanted to make sure I showed you some of the definite integrals. So I didn't finish all the indefinite integrals, but I need to show you how a definite integral works. like 55. So, oh, why don't I start off with 53? Yeah, 53. Integral from 0 to 1 of cosine pi over 2t dt. Okay. Now for this time, I'm actually going to put t equals 0 and t equals 1. You might say, well, that's obvious. It's dt, but follow my logic anyway. I'm going to put t equals 0, t equals 1. By the way, you don't have to write it if you don't want to. I suggest you do. It'll keep you from getting mixed up. Or put it this way. When people put t equals 0 and t equals 1, they're much less likely to make a mistake than if you don't put it. Okay, so I recommend putting it. I put it, as you can see. Okay, now the beginning part's the same. Let u be pi over 2t. du is pi over 2 dt. So that's the same. Also the same, I need to put pi over 2 inside, which means 2 over pi outside. So that's the same. So the next step, instead of cosine all this stuff, it's going to be cosine u. Instead of pi over 2 dt, what is pi over 2 dt? du. That's the same. But notice what's happening. This is with t equals 0, t equals 1. It would not work if I put t equals 0 and t equals 1 here and have cosine u du, because the new problem would be in u, but my two limits would still be in terms of t. So when I have a definite integral, I will change these t values to the corresponding u values. How do I do that? Well, I look at the relation u equals pi over 2t. So what you need to do now is plug in 0, plug in 1 for t, right here. Find the corresponding u values, and then I'm going to integrate as u goes from something to something. Okay, so here's how you do it. Plug in t equals 0. What do you get? Pi over 2 times 0, 0. Plug in 1, u equals pi over 2. All right, that means when I integrate with respect to t, when t goes from 0 to 1, u goes from 0 to pi over 2. So look at the brand new problem. Instead of cosine pi over 2t, by means of this substitution, I have cosine of u. Pi over 2 dt gets changed to du. Yes, I have a 2 over pi out front. And the limits are now going to be u values. Because when t goes from 0 to 1, u, that's why I write u equals here again for emphasis. The whole problem is now going to be in u. I'm completely burning the bridge, so to speak, of t. I'm not going to go back to the original t. The whole problem is going to be in u. So u equals 0 to pi over 2. Now I'm good. The whole problem is going to be in u. So I change t to u. I change dt to du. And my limits, which used to be with t, are now going to be in u. So in this case, unlike the indefinite integrals, right? Remember the indefinite integrals? Once you had an expression with u, right? I had to change it back to x. No need to do that for definite integrals. For definite integrals, once you get u, du, and even these limits are u, that's why for emphasis I put u equals here. So how come you never wrote it before? Well, before there was only one letter. It was always x dx, or w dw, or theta d theta. You didn't have to wonder, I wonder what these are, what variable. There was only one variable to talk about. But now, since we're switching t and u, that's why right now I emphasize write t equals blah, 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 blah. Okay, because these are the variables t. But now when I switch over to u, we're going from something else to something else maybe. Okay, so now the whole problem's in u. Okay, that's u, that's du. These limits are u. I do not have to go back to the original t. So just take it from here. All right, 2 over pi. What's the integral of cosine? Careful. Not negative sign. Negative sign is the derivative, but antiderivative, sine u. Okay. Recall this is a definite integral. So what do I do for definite integrals? Don't need to put the plus c. The funny looking s, which was on the left side, migrates over to the right side and straightens out. So it's like that. Okay, you can factor out the 2 over pi. Okay, sine of pi over 2 minus Sine of 0. Sine of pi over 2 is 1. Sine of 0 is 0. 1 minus 0 is 1. Final answer is 2 over pi. Okay, so this is what you do for definite integrals. Okay, we will change the limits also. So this is before same. Du is the same, but now the new stuff for definite integrals is to change the limits. Okay, so instead of integrating with respect to t, I integrate with respect to u. These two limits might be different. Okay, so the whole problem is no longer in t. The whole thing is in u. No need to switch back to the original variable, which I had to do for indefinite integrals, right? You never leave your answer as du and u, so you cannot leave your answer like that, right? I mean, just stop and think about it. That doesn't make sense. The whole problem started off with x. How can you leave your answer with u, right? That's why we have to switch back. But for definite integrals, we do not have to switch back because we'll have the new limits in u, or whatever letter it happens to be. Okay, 55 is another example. So 255. Take a look here. Yeah. Okay, integral from 0 to 1, cube root of 1 plus 7x. Okay, so I don't want something complicated behind my finger. I just want u. So let u be 1 plus 7x. What's the derivative of 1 plus 7x? 7. So du equals 7 dx. So same game as over here. Put a 7 inside, 1/7 outside. But now, as x goes from 0 to 1, what happens to u? So I plug in. So x equals 0, u equals something. X equals 1, u equals something. I'm temporarily covering it. How do I get these? I just plug in. So what happens when x is 0? Put a 0 here. 1 plus 0, 1. Plug in x equals 1. 1 plus 7, 8. Okay, so my new integral isn't going to go from 0 to 1. Those were for the variable x. Because u and x are related by this function here, when x goes from 0 to 1, u goes from 1 to 8, a much, much different interval than 0 to 1. So notice I has a 1/7 in front. Cube root of, not 1 plus 7x, but cube root of u. 7 dx is my du. And notice you must change over. It's not 0 to 1 anymore, because 0 to 1 are for which variable? X. I'm no longer doing x. I'm now doing u. 1 to 8. So now I'm good. And you notice I didn't write u equals this time. You know, it's optional, I suppose. But when x goes from 0 to 1, u goes from 1 to 8 by means of this relation. Okay, now the rest is pretty straightforward. So 1/7 u to the 1/3 du. So 1/7 integral of u to the 1/3, u to the 4/3, 1 more than 1/3, right? 4/3 divided by 4/3 means times 3/4. Okay, this comes out to be 3 over 28, which I'm factoring out. Okay, plug in 8, 8 to the 4/3. Minus, plug in 1. There's a 1 there. Should have some kind of separation there. The number 1. Minus 1 to the 4/3. Well, 1 to anything is 1. 8 to the 4/3 means cube root of 8, 2. 2 to the 4th, 16. 16 minus 1, 15. Final answer, 45 over 28. Okay. Okay, problem 59. So again, these are definite integrals. E is in 1 over x squared dx. So how do I know what to substitute? Well, a good guess is, you know, I don't want e to a mess. I'd rather just have e to the u. So how about let this be u? And believe it or not, the derivative of 1 over x is almost 1 over x squared. So what do you mean by almost? I'll show you in a second. So let that be u. U equals 1 over x, which is x to the minus 1. Du is negative 1, or negative x negative 2 dx, which is negative 1 over x squared dx. So it's almost the derivative. I have 1. See, I don't see the 1. You can always put a 1 in, right? I have 1 over x squared dx. I need negative 1 over x squared dx. Simple. Multiply inside and outside by negative 1. That way, the next step in green, that's going to be u. Negative 1 over x squared dx. Negative 1 over x squared dx. This green stuff is going to be my du. And x is going from 1 to 2. Figure out what u does. Since u is 1 over x is 1, u is 1. X is 2, u equals a half. So my new integral is going to be e to the u, du, perfect. Okay. But let's see, 1 corresponds to 1, so 1's on the bottom, 2 corresponds to half. So negative integral from 1 to a half. That's backwards. We usually like to have the smaller number here and the bigger number here. No big deal, especially since there's a minus here. And this happens a lot, by the way. Just change it to a positive, flip these two around, and now you have the best of both worlds. It's now positive, and smaller numbers here, bigger numbers here. Right? So instead of integrating from 1 to a half, which is kind of backwards, we usually like the smaller number here and the bigger number here. Just apply the negative sign, put the 1/2 here and the 1 here, and that's perfect. Okay, integral of e to the u is itself. E to the u from 1/2 to 1. Plug in 1, you get e to the 1, e, minus e to the 1/2. So that's e minus radical e. Final answer. Okay. 67 actually works differently. You haven't seen anything like this yet. So 67 is new. And there's some ones before that, the indefinite integrals that are kind of like this also. So I'll show you more tomorrow, but I was going to stop after 67. And what time is it? Not quite 10 to. Okay, so I'll be done in a few minutes, at which point, if you want to ask me questions, you may. Otherwise, we're done for the day. Okay, x radical x minus 1 dx. And let's see, I make a note that this is like number 47. So when you try 47, which is 47 is indefinite integral, but it's the same principle. Okay. How do I substitute? I mean, the derivative of x minus 1 is 1. Okay. What we're really going to do is say this. I have a complicated expression. Well, x minus 1 is not that complicated, but more complicated than this. After I do my substitution, this will be nice. This will not be nice, but at least this is raised to the first power. Right? So I want the square root to be nice. I don't mind if this is not nice. Okay, so u equals x minus 1. Du equals dx, that's nice. And I need to solve for x. X is equal to u plus 1, right? Add 1 to both sides. Right, now I plug in. X is going from 1 to 2. If x is 1, put a 1 here. U equals 0. If x equals 2, put a 2 here. That means u is equal to 1. So my new integral isn't going to be from 1 to 2. It's from 0 to 1. What's x? U plus 1. Radical x minus 1 is radical u. And then du is the same as dx. All right, so look at what happened. More complicated, less complicated. I change it into more complicated, less complicated. That's okay because I can now distribute easily. Right? Remember, radical u is u to the half. So u to the 1 times u to the half, u to 3 halves. 1 times radical u, u to the half. And there we go. So integral from 0 to 1. Notice the 0 and 1 are for which variable? U. dx is now du. Everything's in u. I don't have to switch back to the original x. Okay, u to the 5/2 divided by 5/2 times 2/5. U to the 3/2 times 2/3 from 0 to 1. Plug in 1. 1 raised to anything is 1. 2/5 plus 2/3. Minus plug in 0 is even easier. 0 to that is 0. 0 to that is 0. 0 times that is 0. It's 0. So 2/5 plus 2/3. Common denominator is 15. Multiplied by 3 over 3. 5 over 5. Final answer is 16 over 15. Okay. And there we go. Okay, so I've shown you some definite integrals with substitution, but so indefinite integrals and definite integrals. Okay, I'll stop there. I'll do more tomorrow, but now you've seen every type of problem that we need to do. So tomorrow I was going to go back and do some more of these types of problems, and then I'll be done. And Wednesday you can ask questions for the test, and Thursday's the test. All right, so now that I'm finished, let me check the chat and see if anybody has questions. I think somebody did. Let's see. Okay, 5.5 number 19, somebody asked for. Let's see what that means about. .5 number 19. Looks like a bunch of letters. A plus bx squared. Radical 3ax plus bx cubed dx. Okay. When it's written like this, the only variable is x. A and b are considered constants. Okay. So keep that in mind. Okay. So just pretend A is a number. And I notice this is cubed. That's squared. So a good bet would let this be u. So let's try it. U equals 3ax plus bx cubed. Du equals, okay, I know I see a whole bunch of letters, but A is a constant, B is a constant. Okay. So what's the derivative of 3ax? 3a. What's the derivative of bx cubed? 3bx squared dx, like that. And I can factor out the 3, a plus bx squared dx. And what do you know? A plus bx squared, a plus bx squared. There's a 3 that's missing. That's okay. We know the way it works. 3 inside, 1/3 outside. Okay, so now all of this is going to be my du, and all of this is going to be my u. Okay, so my integral now becomes 1/3 integral 3a plus b squared, bx squared dx. 3a plus bx squared dx is now my du. All the numerator is du over radical u. 3ax plus bx cubed. Just like this. Okay. So 1/3 integral of u to the negative 1/2 du. By the way, watch out. This is not your natural log. Natural log is just du over u, or 1 over u du. Anything else, use the power root. So write that as u to the negative 1/2, right? So u to the positive 1/2 divided by 1/2 means times 2, right? And 2/3. Okay, and something to the 1/2 means square root. Okay, so it's square root of u, but what's u? U is all this stuff. ax plus bx cubed, and that's my final answer. Okay, so maybe this one throws people off because of the extra letters, but that's part of the reason why we write dx. Dx means x is the variable, a and b are constant. By the way, we could change this problem completely if I said dA. If it's dA, then all of a sudden a is the variable, x and b are considered constants, right? All right, so as it stands, that looks like my final answer. Okay. All right, I think I've caught up. Let me look at the chat. Okay. So I think that's about it, folks. So anybody have a quick question? Otherwise, we still have tomorrow and Wednesday in preparation for the test. So I think we're good. Anything else? All right, then we'll call it a day, folks. All right, so have a good afternoon. We'll see you tomorrow. So tomorrow I'll do a lot more problems from 5.5, hopefully. And then Wednesday we'll review for the test. All right, have a good day, everybody. We'll see you. Okay, bye, everyone.